Picture this. It is like 2 in the morning. The glow of your IDE is the only light in the room, and you're just staring at a blinking cursor.
Oh yeah, the classic late-night coding
All
session.
right. You hit enter on a prompt, and in that incredibly brief silence, just before the text starts streaming across your screen, there's this massive, invisible machinery grinding away.
It is wild when you actually stop to think about it.
It really is. I mean, we are talking about the final microsecond before an AI model actually speaks. It's staring down a vocabulary of maybe 30,000, sometimes even 100,000 distinct tokens.
And out of all those thousands of possibilities, it has to make a single choice. Just one.
Exactly. The sheer scale of that decision-making process is just staggering.
Yeah, it's a phenomenal amount of calculation to execute in, what, a fraction of a second. The model isn't just heuristically picking a word that seems vaguely appropriate.
Right, it's not guessing.
No, not at all. It is mathematically scoring every single possible word in its entire universe simultaneously. It's evaluating exactly how well each one fits the sequence.
So, if you're a software engineer dialing in to really understand the machine, this deep dive is absolutely for you. We're demystifying the ultimate gatekeeper of AI decision-making. We're talking about the Softmax function.
A big one.
The big one. We are going to unpack the mechanics of large language models to understand not just the theoretical math, but how those API parameters you're constantly tweaking, temperature, top, how they actually manipulate the underlying code at runtime.
Because they aren't just magic dials, they are literal math equations.
Okay, excellent. Okay, let's unpack this.
Yeah.
Before we get to the function itself, we have to look at the raw problem it's designed to solve.
Right, the raw output.
Yeah. When a neural network finishes all its deep computation at the very last layer, it outputs raw numerical scores for every single token in the vocabulary. And in machine learning, these are called logits.
Logits. And logits on their own are effectively completely unusable for final decision-making.
Because they're just arbitrary numbers, right?
Yeah, pretty much. If you inspect the output array for a specific token, you might see a logit of, 5.2. Another token gets a negative 1.3. A third gets 12.7.
So they're just unbounded floating point numbers.
Exactly. They can be massively positive or deeply negative. And from an engineering perspective, you just cannot build a reliable, probabilistic selection loop around an array of unbounded, unnormalized integers and floats.
Right. You can't roll a die if the sides of the die are like -5 and +20.
Exactly. To make a choice, what the system actually needs is a strict probability distribution. We need a set of positive numbers that represent percentages. And this is key. They must sum up perfectly to 1.0.
A clean 100%.
Yep.
Now, I feel like the natural instinct for any programmer writing a normalization function is to just keep it simple. Find the lowest negative number, add its absolute value to everything so all the numbers are positive, and then just divide each individual score by the total sum of all the scores.
It's the standard normalization approach.
Right. It's straightforward math, and it gives you a perfect 100% distribution. But applying that logic here fundamentally breaks the language model.
It completely ruins it.
Because simple division treats all numerical differences exactly the same. Like, if the model scores the optimal word cat as a 10 and the slightly less optimal word dog as a 9, basic normalization distributes the probability almost evenly between them.
And in language generation, a 1-point difference in a raw logit is not a minor preference.
Right, it's huge.
It often represents the cavernous gap between a perfectly grammatical, coherent sentence and just complete synthetic gibberish. You do not want a selection function that treats a 10 and a 9 as competitive equals.
Right, which is exactly the talent show analogy from our source material.
Oh, I love that analogy.
It's so good. Imagine a talent show where the judges score contestants on a linear scale from 1 to 10. Simple normalization is like those judges' scores. A 9 and an 8 look incredibly close on paper.
Almost tied.
Yeah. But Softmax is the equivalent of the fans voting with their actual wallets. It creates this massive exponential funding gap that viciously separates the top-tier talent from the rest of the pack. It basically turns a linear advantage into an absolute monopoly.
What's fascinating here is how that mathematical amplification perfectly shapes the model's confidence. Let's actually run those numbers.
Yeah, let's hear it.
If your raw logit is 10, the exponential of 10 is roughly 22,000.
Okay.
But if your competing logit is 9, the exponential is only about 8,000. So that innocent-looking 1-point difference in the raw score just translated into an almost 3-to-1 ratio in final probability.
Wow.
And if another logit in the array was a 5, its exponential is merely 148. So a 10 versus a 5, which looks like a simple 2-to-1 ratio in linear math, becomes a staggering probability ratio of 150 to 1 after softmax.
That is aggressive.
Very. It brilliantly suppresses uncertain predictions into the statistical floor and sharply elevates the confident ones.
So, to put that in a practical context, imagine a tiny vocabulary array of, say, 5 tokens. The cat, sat, on, dog. Let's say cat gets a 5.0 raw logit, while dog gets a 4.5.
A tiny difference.
Right, a half-point difference. But after the softmax function runs, cat commands almost 60% of the probability mass, and dog drops down to 36%. A half-point raw difference becomes a landslide victory.
Mathematically, it is exactly what we want. But looking at the implementation, computing e to the power of these numbers introduces a massive, fatal hardware problem.
That's because of the exponents.
Exactly. If e to the power of 10 is 22,000, and a model outputs a perfectly reasonable raw logit of, say, 1,000.
Which happens all the time in large models.
Right. Computing the exponential of 1,000 is going to trigger an immediate integer overflow. A standard processor utilizing floating point architecture simply cannot represent a number that astronomically large.
So it just breaks.
Left unaddressed, the function would return a nan, not a number error.
And the entire application would crash instantly.
Boom. Done.
So this obviously requires a structural engineering workaround. To achieve numerical stability, developers implement this critical subtraction trick before calculating any exponentials.
Yes, the stability trick.
You basically scan the array of raw logits, locate the absolute maximum value, and then subtract that exact maximum value from every single logit in the array.
Yep, that's the standard fix.
Wait, if we are modifying the raw inputs by subtracting a massive constant from the entire dataset, aren't we changing the underlying numbers before the core algorithm even runs? As a developer, altering input data just to satisfy a hardware constraint usually corrupts the final output.
It usually does.
Yeah.
But the beauty of this specific function is that it doesn't corrupt anything.
Really?
Yeah.
Right.
Because of the mathematical properties of exponentials and division, subtracting a constant from every input effectively factors out and cancels itself perfectly when you divide by the sum of the exponentials.
Oh, that's incredibly elegant.
It is. The mathematical outcome, the final probability distribution, remains identical down to the last decimal. But the impact on the hardware execution is profound. Because you subtract the maximum logit from the entire array, the largest logit becomes exactly 0.
Oh. And since the exponential of 0 is 1, you have fundamentally capped the ceiling of your calculation.
Exactly. The largest possible value the CPU will ever have to compute an exponential for is 0, yielding a perfectly manageable 1.
That's brilliant.
And every other logit in the array becomes a negative number. And the exponential of any negative number safely and predictably approaches 0 without ever risking an overflow.
So you neutralize the hardware limitation entirely.
Completely. You prevent the crash, and you maintain mathematically flawless probabilities. It is a mandatory optimization that literally every systems engineer implements when building these models from the ground up.
Okay, so the foundation is solid. We have a stable, crash-proof function that translates raw neural network outputs into clean probability percentages. But when you're actually integrating an API into your own software, you rarely want just the rigid baseline output.
Right, you want control.
Exactly. You need a way to modulate the behavior, like a volume knob for creativity. Which brings us to the most ubiquitous parameter in AI development, temperature.
Temperature. It is essentially a scalar value that manipulates the raw logit before they are ever passed into the softmax function.
Before softmax, okay.
Right. The mechanism is incredibly straightforward. You divide every raw logit by the temperature value, traditionally represented as T.
Simple division?
Yeah. If T is set to 1.0, you are dividing by 1, the logits remain unchanged, and you get the model's standard baseline distribution.
But if you drop the temperature to something like 0.5, mathematically, dividing a logit by 0.5 is identical to multiplying it by 2. So you're scaling all the raw numbers up. And because softmax is driven by exponentials, making those raw numbers larger violently amplifies the differences between them.
Violently is the right word.
The resulting probability distribution becomes incredibly sharp and peaked. The top token monopolizes almost all the probability, leaving virtually nothing for the alternatives.
Conversely, if you raise the temperature to 2.0, you are basically dividing all the logits in half.
Okay.
A logit of 10 becomes a 5. A 9 becomes a 4.5. The absolute differences between the scores compress.
They get closer together.
Right. When these compressed scores are fed into the softmax exponentials, the resulting probabilities flatten out significantly. Tokens that the model originally deemed highly improbable suddenly capture a meaningful slice of the percentage pool.
The source material visualizes this using the mountain landscape zoom analogy.
That's a great way to picture it.
Right. Think of temperature as your camera's zoom level on a topographical map. Lowering the temperature to point 0.1 is zooming all the way in on the absolute highest peak.
Just laser focused.
Yeah. That single summit fills your entire field of view. The surrounding foothills aren't even visible. The top choice just dominates entirely.
Yep.
But raising the temperature to 2.0 is zooming way out. The landscape visually flattens. The highest peak is still technically the highest point. But everything blends into a rolling plane where every token seems to have a decent elevation.
If we connect this to the bigger picture, it is vital to understand that the model's internal logic has not changed whatsoever.
It hasn't.
No, the neural network still inherently calculates that cat is the optimal next word. The underlying logics are identical.
Oh, I see.
Adjusting the curvature does not alter what the model knows. It strictly dictates how heavily the system should weight the model's confidence versus the introduction of statistical randomness.
Okay, so we shaped the odds. The array of percentages is finalized. But a percentage array is not a word. The system still has to execute a definitive selection and pull the trigger on a single token to print to the screen.
Right, it has to commit.
And to make that final call, the architecture forks into two distinct methodologies. The first is greedy decoding.
Greedy decoding is basically the operational equivalent of setting your temperature to absolute zero.
Just freezing it.
Totally. There is no gambling and there is no variance. The algorithm scans the final probability array, identifies the single highest percentage, and selects it.
Period.
Period. It operates with 100% determinism. If you feed it the exact same prompt, it will return the exact same output every single time.
Now, logically, if the model's top choice represents its mathematically verified best guess at the perfect next word, you'd assume greedy decoding would yield the most eloquent, perfect text.
Right. You would think so.
But in practice, running an LLM on strict greedy decoding frequently produces incredibly flat, sterile language that inevitably gets trapped in repetitive, cyclical loops. Why is that? How does picking the best word at every single step somehow result in a structurally inferior paragraph?
It's a great question. And it exposes the fundamental difference between a local optimum and a global optimum in sequence generation.
Local versus global.
Right. Greedy decoding is strictly locally optimal. At any given microsecond, picking the word "the" might be the safest, highest probability local choice based on the preceding sequence.
Sure.
However, human language is not a series of isolated, mathematically safe bets. Frequently, selecting a slightly less probable word in the present moment, perhaps a highly specific adjective or an unconventional verb, opens up a linguistic pathway that allows for a drastically more coherent, nuanced, and globally optimal sentence structure 5 words down the line.
Oh, that makes so much sense.
Because greedy decoding is entirely risk-averse, it refuses to make those slightly suboptimal local choices, completely cutting itself off from globally superior text generation.
It's totally analogous to a chess engine program to only evaluate one single move ahead.
Exactly.
Like, it will consistently take the most obvious, unprotected pawn on the board right now. But in doing so, it completely blinds itself to a brilliant, complex, 6-move checkmate sequence.
Spot on. To achieve that global optimum and generate truly natural language, the system relies on the second methodology, sampling.
Sampling.
Yeah. Sampling introduces stochasticity by rolling a computationally weighted die. If your Softmax distribution assigns cat a 60% probability and dog a 36% probability, the system does not automatically default to cat.
It rolls the die.
He rolls the die. It generates a random number. 60% of the time, that random number dictates cat. But 36% of the time, the model actively selects dog.
Even though it wasn't the top choice.
Right. This is the mechanical reason why you can send identical prompts to a chatbot API and receive entirely different essays in return. The raw logics were the same. The Softmax exponentials were the same. But the random number generator charted a different path.
And that single stochastic dice roll triggers a massive cascading effect.
Oh, massive.
The moment the algorithm selects dog instead of cat, that word is appended to the context window. The next token is now predicted based on the presence of dog, and the entire grammatical universe branches off in a new direction.
A totally new timeline.
Right. But rolling a die introduces a severe vulnerability. If a developer uses a high temperature, they've artificially flattened the probability landscape. Tokens that mathematically had a 1% chance of fitting the context now have a mathematically viable shot at being selected.
Which is dangerous.
Exactly. If the random number generator hits an unlucky streak, the model will output a completely nonsensical, grammatically broken word. So to build a robust application, you have to constrain that randomness.
You absolutely have to. You need programmatic filters to truncate the tail end of the distribution. And the most historically prevalent filter is top-can sampling.
Copcha.
Yeah. The algorithm is rudimentary but effective. Before the random die is rolled, you sort the array of probabilities and simply slice it at a hard integer. Right, if you set top cake to 50, the system preserves the top 50 most probable tokens, aggressively deletes the other 99,950 tokens from the vocabulary array, recalculates the probabilities among the surviving 50 so they sum back to 100%, and then rolls the die.
I mean, the logic makes sense until you analyze the edge cases.
Right.
Imagine the model is predicting the next token for the phrase, the color of the car was. There are easily 200 grammatically and logically valid colors.
Easily.
But Top K operates on a hard threshold. By setting it to 50, you're arbitrarily deleting 150 perfectly valid options from the model's reach.
You're restricting creativity unnecessarily.
Exactly. Conversely, if the sequence is the capital of France is, there's really only one structurally valid next word.
Paris.
Right. But Top K blindly forces the system to keep 50 options active, meaning the die is rolling against 49 garbage tokens.
Top is architecturally rigid. It lacks the ability to respect the semantic context of the prompt. And this fundamental flaw drove the industry toward top sampling, commonly referred to as nucleus sampling.
Nucleus sampling?
Yes. Instead of restricting the candidate pool by a fixed number of tokens, top restricts the pool based on cumulative probability mass.
Okay, here's where it gets really interesting for developers writing the implementation. With top, you define a float threshold, usually around 0.9.
Right.
The algorithm sorts the probabilities in descending order and begins iterating through the array, keeping a running sum of the percentages. The exact moment that cumulative sum crosses the 0.9 threshold, the algorithm slices the array.
It just cuts it off.
Yeah. Every token processed up to that point forms the nucleus of valid choices. Every token after that point is simply discarded.
It creates a brilliantly dynamic filtering system. If the model is highly confident, returning to the capital of France example, the word Paris might possess a 95% probability right off the bat.
Right, so it's already over 0.9.
Exactly. The cumulative sum immediately exceeds the threshold on the very first iteration. The nucleus restricts itself to a single token, effectively behaving like greedy decoding when certainty is absolute.
That is so smart.
It really is. But for the car killer example, where probability is heavily diluted across hundreds of valid adjectives, the algorithm might iterate through 200 tokens before the running sum finally reaches 90%.
So the size of the candidate pool organically breathes. It expands and contracts based entirely on the model's real-time confidence metrics.
Exactly.
And it is crucial to understand that these parameters aren't mutually exclusive. They execute sequentially.
Right, they stack.
Your application applies temperature first to scale the raw logits. Then Softmax converts them into a normalized percentage array. Then top iterates through that array to draw the boundary around the nucleus. And finally, the algorithm rolls the weighted die.
Yes.
If you set a very low temperature, like 0.1, your top filter might not trigger at all because the exponential amplification has already assigned 99% of the probability to the first token.
But when you configure a high temperature to encourage creative output, top acts as your ultimate architectural safety net. It guarantees that even when the model's distribution is aggressively flattened, the random selection is still strictly confined to the pool of tokens that collectively constitute the top 90% of logical sense.
Okay, so we've thoroughly mapped the standard API execution flow. But researchers and engineers pushing the boundaries of language modeling often bypass these standard methodologies entirely.
They do.
We established that greedy decoding fails because it only looks one move ahead. But what if an architecture requires the global optimization of looking multiple moves ahead without introducing the inherent unreliability of a stochastic die roll?
That specific requirement is fulfilled by an algorithm called beam search.
Beam search.
Yeah. Instead
Why?
of committing to a single token or relying on a random sample, beam search explicitly maintains an array of multiple branching paths in memory simultaneously.
Like parallel universes.
Exactly. You define a beam width parameter, often denoted as B. If D is 5, the model evaluates the first step and locks in the top 5 distinct starting words. Then, for every single one of those 5 active paths, It runs a forward pass to predict the next token.
Wow, that's a lot of passes.
It calculates the joint probability for all the resulting two-word combinations, sorts them, keeps the top 5 most probable overall sequences, and aggressively prunes the rest of the tree. It repeats this process continuously, navigating the vast computational maze by always preserving the 5 most globally promising textual branches.
So the resulting output is highly deterministic. Executing beam search multiple times yields the exact same sequence,
Precisely.
which makes sense. Historically, it was the gold standard algorithm for applications like Google Translate, where generating a creative interpretation of a legal document is unacceptable. You strictly want the most mathematically accurate global translation.
Right, you don't want your translator getting creative with your contracts.
Exactly. But for modern conversational interfaces, computing multiple forward passes for every single step is vastly too expensive, and the deterministic nature makes the dialogue feel a bit robotic.
It does, and this raises an important question regarding the training phase itself. Modern generative models depend heavily on sampling to produce varied, natural text. However, from the perspective of calculus and machine learning optimization, a random die roll is a discrete, discontinuous operation.
Meaning what, exactly?
It operates like a staircase function. You cannot calculate a slope or a derivative on a staircase. If you cannot calculate a derivative, you cannot run backpropagation. The gradients drop to 0.
Oh, wow.
So how do AI researchers train networks end-to-end when the final selection step mathematically blocks the learning algorithm?
Well, this is solved by an incredibly elegant mathematical bridge known as the Gumbel Softmax trick.
A lifesaver of a trick.
To circumvent the discrete nature of a die roll, engineers inject a highly specific statistical variance, Gumbel distributed noise, directly into the raw logits before they reach the softmax function. They then drop the temperature parameter to a fraction above 0.
That combination is genius. The addition of the Gumbel noise stochastically shifts the logit values, while the near-zero temperature forces the softmax output into an incredibly sharp, spiky distribution.
Okay.
Visually, it looks almost identical to a hard, discrete selection where one token holds 100% of the probability. But mathematically, because it's constructed from continuous noise and exponentials, the underlying curve remains perfectly smooth.
So it maintains a calculable slope.
Exactly. This allows the backpropagation algorithm's chain rule to flow unimpeded right through the simulated discrete choice, updating the weights of the entire neural network. It's a foundational technique for training models via reinforcement learning from human feedback.
Okay, so we've examined softmax extensively as the final gearway, right? The absolute last computational step before text hits the screen. But if we trace the architecture backward, deep into the internal layers of the transformer block, we find the exact same selection mechanism operating continuously.
Oh, yeah. Softmax is everywhere.
Softmax is literally the beating heart of the attention mechanism itself.
Absolutely. Deep inside the network, the model has to determine which specific words in your input prompt are contextually relevant to each other. To do this, it computes dot products between vectors, generating raw attention scores that dictate the relationship strength between every pair of words.
But exactly like our final output layer, these internal attention scores are unbounded raw numbers.
Right, they must be converted into normalized percentages of attention.
So the architecture routes them directly through an internal softmax layer. It serves the exact same amplifying purpose. If the internal vector for the word bank strongly aligns with the vector for river, the raw dot product is high. Softmax processes that high score, applies the exponentials, and ensures that specific contextual connection receives the lion's share of the model's mathematical focus.
Yep.
But during text generation, models utilize a causal mask to physically prevent the system from looking ahead at future tokens. We enforce that restriction by assigning those future positions an attention score of -infinity.
And Softmax handles that computational edge case flawlessly. The exponential of -infinity is exactly absolute zero. The Softmax layer effortlessly converts those restricted future connections into a flawless 0% probability, cleanly erasing them from the attention matrix without disrupting the core sum-to-1 distribution requirement.
There is one final scaling optimization inside that internal attention mechanism. Before the raw dot product scores are fed into Softmax, they are divided by the square root of the dimension size, the score TK factor.
Right, the scaling factor.
In massive language models, computing dot products of high-dimensional vectors drastically increases statistical variance, resulting in extremely large numerical scores.
And if you feed extremely large numbers into Softmax, the exponential amplification goes into overdrive. The resulting probability distribution becomes an absolute step function. One token gets 99.99% and everything else gets 0.
It's totally flat.
Yes, and when the output curve is that completely flat at the top, the derivative drops to 0. This causes what engineers call gradient saturation. If the gradient is 0, the neural network literally cannot update its weights.
The learning process completely stalls.
Completely. Dividing the scores by that square root compresses the variance back down to a manageable baseline, ensuring the numbers fed into Softmax remain small enough to produce a gentle curve with a calculable, healthy slope.
So what does this all mean for you, the software engineer, currently tweaking these dials in your IDE? From an integration standpoint, here are the actionable takeaways.
Let's hear them.
If you are leveraging an LLM to generate precise syntactic code or solve deterministic math equations, drop your temperature to 0. You want greedy decoding to ensure the highest mathematical confidence without variance.
Absolutely.
If you're developing a conversational agent that requires a balance of natural phrasing and reliability, configure temperature around 0.7 and set top hap to 0.9 as your dynamic safety net.
The standard chat defaults.
Right. And if you're building a tool for divergent brainstorming or creative writing, push temperature to 1.0 or 1.2, but absolutely ensure top hap remains active to filter out the long tail of synthetic hallucinations. Avoid anything over 2.0.
Ultimately, the softmax function operates as the supreme arbiter of the system. It is the precise mathematical coordinate where cold, multidimensional array computation is finally collapsed and transformed into a distinct, human-readable choice.
It takes tens of thousands of floating point numbers, subjects them to aggressive exponential amplification, safely navigates hardware integer overflow limits, modulates its confidence against your temperature setting, dynamically truncates its options through nucleus probability thresholds, and finally executes a stochastically weighted die roll.
And it executes this entire sequence for every single word.
Just incredible. But here is a final thought to mull over before you dive back into that late-night coding session. We've spent this entire deep dive meticulously analyzing the intricate, delicate mathematical architecture of this specific function. But what happens to the output when we take this exact same softmax arbiter, leave the math completely unchanged, but house it inside a neural matrix that is exponentially larger?
Oh, that's the big question.
What happens when we feed that precise equation an ocean's worth of training data and back it with a nuclear reactor's worth of GPU compute? The scaling laws of machine learning suggest that simply making the matrix bigger fundamentally changes the rules of what the algorithm is capable of understanding. We will leave you to ponder the implications of that scale. Until next time, keep tinkering, keep dialing in those parameters. Because out there in the dark, in that final microsecond before the model speaks, the math is waiting.